Physics 1101, Chapter 4A lecture. On Newton's laws of motion. Which were developed by Isaac Newton back in the 1660s and 1680s and are the basis of all forces we have today. So, we'll start off with that. This will be part of exam 2, which has the last part of chapter 3, and then 4 and 5. Okay? So, we'll go through the 3 laws. And some of the things will be related to theirs. So, first law. First is a motion object in motion will stay in motion. All right? Meaning if we push an object in space on a frictionless surface, all right, we'll get into friction. So frictionless, meaning there's nothing hold back. It will move in a straight line with a V is constant forever. All right, it'll just go until it hits something. So that's what we mean. This also means that there's no force on it. Net force is 0. So the same thing as you throw something into space, it'll just glide forever and ever without slowing down. This is contrary to what people thought, because back in the long time, when we see anything, if you push something, let's say it's a roll of tape, I push it on this book, it stops almost immediately. So it was thought, and it takes force to keep it going. So it was thought that originally objects required a force to keep them going. Well, this is only because in the real world, friction, as we'll see, is a very significant factor. But if there was no friction, it's much like seeing a puck on a hockey rink. You hit it and it just goes almost without slowing down at all, because there's very little friction or anything slowing down. So it'll go at a constant speed. Constant velocity, I should say. All right, second law is then if there is a force applied, the force is equal to the mass times the acceleration, where this is in units of newtons, this is in units of kilograms, and this is meters per second squared. So Newton, we'll be introducing the Newton, named after Isaac Newton. And the best example with this is with gravity, where force acceleration of gravity is G, and if we use, G is 9.8 meters per second squared, and it's downwards. If we have a 1 kilogram object times 9.8, that would equal to 9.8 newtons. All right, so 1 kilogram object weighs about 9.8 newtons. Now, for just sense of understanding, 1 kilogram on Earth weighs about 2.2 pounds. So one pound is approximately 4.5 newtons. All right. So 1 pound is about 4.5 newton. All right. So that's only for sense of, get a better idea of that. But we're only going to be using the Newton. All right. So We're not going to get into the other things. So an object, if it has a force on it, will have an acceleration with it, given by this expression. Okay. All right, let's see. And then a third law, I'll do this. Third law is action, reaction. And we can see this very clearly with the picture at the front of the book, which shows a rocket is, in this case, the space shuttle launch. And you see the red on the right. The fuel is ejected at rapid speed out the back end. And the result, the rocket goes forward into space. Now this is, again, contrary to, this high concept of this, even 100 years ago, was thought that space travel is impossible because how do you move, right? The only way you can kind of move, like if you push, like for me, if I just push my hand that way, I don't go anywhere, right? But if I push my hand off the wall, I will move. I push this way, I go this way, right? If I push this, it moves that way. So it was thought that things in space could never travel because there was nothing to push against. So it was thought that rockets needed the fuel ejected to push against the atmosphere to be able to go into space. But we know now that actually space travel works better in space because there's no air to resist the motion. So you throw it out as fast as you can to the back and the rocket goes the other direction. So this is the whole point of with these rockets, is to have fuel going out as fast as several kilometers per second, which accelerates the rocket in the other direction. So this is Newton's third law of motion, action, reaction. So force that way has an equal and opposite force in the other direction. So this is the force, and we call this the reaction force, and the two are equal and opposite. All right? So those are the three laws of motion. Now we're only going to be dealing with third law of motion, mostly in an intuitive basis, because it's a concept of how things work, but we do in most of the problems will be related to Newton's second law of motion. Okay? So, let me see where I am here. Because I don't want to get too far ahead. All right, well, let's do an example using this. And they got an example in the book, or we can do something like that. We have a car going 60 miles per hour. Oh, roughly 30 meters per second. Let's go 66 miles per hour, which would be 30 meters per second. And, all right, wants to stop in a distance of 55 meters, all right? Make sure I get my calculator. All right. And this car has a mass of 1,000 kilograms. All right, a couple things we'd ask is what is the acceleration? And then what is the stopping force to make this thing stop? All right, so let's do this problem. All right, what do we know? We know X is 55 meters. We know V naught is 30 meters per second. And V final is 0. So we're trying to find the acceleration. So in that case, we go back to our expressions that we have from chapter 2. And in this case, we'd use the expression, because we don't have any time involved here. So it'd be V squared is V naught squared plus 2AX. All right. That's what we'd use. Well, V is 0. This is 30 squared plus 2 times 55 times A. All right, so that would mean A would be rearranging 900 over minus 900 over 110. If I'm not mistaken. Yeah, so if we calculate that, would be 8.2 minus 8.2 meters per second squared. All right? Now, if we want to compare this to, say, a G force, right, G is 9.8 meters per second squared. So this is roughly, this acceleration is roughly 0.8 G. All right, so that's quite a force to stop at 170 feet to go from 70 miles. So it's quite a stopping force. You would definitely feel this. Right, now the force on this thing would be F equals MA, which would be 1,000 times minus 8.2, which would be minus 8,200 newtons. So that would be the force required to stop this car, all right? Which would be, in this case, most likely by friction with the road surface. All right, now we'll get into later, all right, is this actually gonna work? Can we actually do this based on conditions? So we'll get into that in a little bit. And all right. Okay, so that's the first part. All right, second part, and then we'll stop here for today as far as this is concerned, because I want to deal with friction in the last part. Maybe I'll do a friction today. All right, so that's one example. Now, we have other cases of forces. All right, we have gravity, which we define as weight, which is m times g. Right? So if you have a 100 kilogram weight object, its weight is 100 times 9.8 or 980 newtons. All right? So let's do, now what we can do with this is deal with this in gravity, which will be an interesting example. Okay. And let's take a person in an elevator, all right? They weigh 100 kilograms, so they weigh 980 newtons, just standing there. Now, if you're in an elevator, you're just standing there. One thing, you don't know whether you're stopped or you're moving with constant velocity, up or down. Because in the elevator, the only thing you can detect is your weight or acceleration. If you're moving at constant velocity, upwards or downwards, you're not going to feel any different. It's the same thing as riding in a train going 200 miles per hour in a plane. You really can't tell any difference because constant velocity means the net force is 0. All right? And so you feel no effect. Constant velocity makes nothing. Now, how will we actually feel something different? Well, if you're in an elevator and you go up, go from the ground floor upwards, you have to accelerate, right? To be able to start going, then you stop, and then you gradually settle out, and then you stop again. So when you go up, you'll go up the stair, you'll go up, so A will be greater than 0 going up, and then you'll slow down and A will be less than 0 before you stop. All right. So if you're, say, standing on a scale, what would you weigh if you accelerate where A is 2 meters per second squared going up? And then when you stop, you're slowing down. Remember, velocity would be up this way. Acceleration is up this direction, but when you're slowing down, A is that way. So A would be minus 2 meters per second squared before you stop. All right, so what would the scale weigh for each case? All right, your weight would be, in this case, in both cases, the weight would be M times G plus A, where we're defining G is 9.8 meters per second squared, and we're calling A is up, is positive, and coming down is negative. All right? So we'd weigh in the first case, the weight would be 100 times 9.8 plus 2, which would be 1,180 newtons. So that's how much you'd weigh, and then when you start to slow down to stop, you'd feel like a reduction in weight. A weight would be M times G plus A, same formula, but that would be 100 times 9.8 minus 2, and that would be 780 newtons, right? The same concept would be if you were free fall, if you're falling. If you're falling, so if you start and you fall, you'd feel acceleration is downwards, is negative, and then when you start to slow down, then you'd feel more weight again. So if you do it the other way around, you'd first feel like, ooh, the weight is falling off from under you, and then when you hit near the floor you want, it starts to stop again. And again, A would be upwards here. So this would be how we would define it, using G is plus 9.8, and up would be positive, and down would be negative. So this is how you can find what the weight, what your weight would be in a accelerating elevator. So that's an interesting problem as far as that's concerned. All right, and this also has to do with Einstein's theory of general relativity, is that you can't tell any difference from an accelerating object or gravity. It's how you can simulate gravity in space is by accelerating an object or a rotating object. Okay, so this is part of section 4.6 in the text. And read through those problems there, all right? Okay. Oh, yeah, while we're at this then, this is also going to be part of the lab. We'll move on to the next part here. We got plenty of time. All right. And this will be the lab. On the Atwood machine. Right? And the Atwood machine was developed by George Atwood. It was actually a way of measuring acceleration, trying to measure forces of F equals ma back before you had any real technology, back to 1700. So if I just drop this without any real technology like a video camera or some measuring device, it's extremely hard to tell what's going on here. It's hard to tell if this thing's actually accelerating. So what George Atwood did was figure out a way to slow the whole process down by using a pulley with two masses on one side, M1, M2, and what we can see is if we have just a single object by itself, M1, the force is M times G, and that would be M times A, and so the acceleration is just G. All right, so it's the same force. Now, in this case, when we have this, it's not, we just have gravity pulling it down. What we have is gravity pulling in one direction, the other direction, but the objects are both being accelerated together. So how would we do this here? All right, so we have F equals ma. All right, so, and in this case, we have both of them attached together. So when one accelerates, this one accelerates down, this accelerates. So they're connected together, so the acceleration is the same. Well, what's the force going to be? Well, this one's pulling downwards, and this one's pulling up, but they're opposing each other. And so I'm going to do, it would be, the force would be M1 minus M2 times G. And if M1 is bigger than M2, it's going to accelerate this way. If M2 is bigger than M1, it's going to accelerate the other way. And so we can get then is the acceleration A is going to be given by M1 minus M2 times G over M1 plus M2 times G. All right. So that's the example there. So let's do one simple example with this. All right. So let's pick M1 is 2 kilograms and M2 is 4 kilograms. All right. Doesn't matter, just pick a couple numbers. And we'll be doing this in the demonstration lab. So it'd be 2 minus 4 times 9.8 over 2 plus 4. So that would be 2 over 6, so it would be 1/3 of 9.8, or roughly 3.3 meters per second squared, and it would be accelerating this way, because M2 is bigger than M1, so it would accelerate this way with A is if you want to call that down, minus 3.3 meters per second squared. Okay, so that's one example of the Atwood machine. And that's what we'll talk about in lab. And it's a very, and the closer they are together, as far as the weights, the acceleration will be much slower. So if they're relatively close, it'll accelerate slowly. You can make some very precise measurements on what's going on. And this is what George Atwood did in the late 1700s when he was trying to make some precise investigations of F equals ma. All right, so that's one example. All right, another example of this, instead of both hanging ones, we can have one where we have a pulley. One's hanging M2, and the other one is just on a flat surface M1. So this is flat, this is hanging. So in this case, what would the forces be? So force is MA. Well, they're both together, so again, they're accelerating together. But what's the actual force? Well, the force is only due to gravity. The only thing pulling this down is M2. So the force pulling would be just M2 times G. And so A would be M2 times G over M1 plus M2, right? And so if you do an example here, where M1 is 2, like we had before, and M2 is 4, then this would be 4 times 9.8 over 2 plus 4. This would be 6.7 meters per second squared. Right? So this is about twice the acceleration in the previous case. So this is a variation of the Atwood machine where you've got one is pulling, the other is horizontal. And that's the case there of that. Now, all right. Last thing we're going to do is we'll talk about the last section. And this will be 4.8, and this will be on friction. And in this case, I'm only going to be doing friction on a horizontal surface. Right? And we define friction is what we call the coefficient of friction times what we call the normal force. The normal force, Fn, is this m times g. Get rid of this pen. So this is just all right, as we call this mu, coefficient of friction. So an example, if we have a weight of 100 kilograms that had a mass of 100 kilograms, the normal force would be 100 times 9.8 or 980 newtons. So, if an example would be, if I have a weight, this weighs 980 newtons, and I'm trying to push it, all right? And depending on the surface, we got certain things here, and I can show you some examples. The table. Right? The table has coefficients of friction. And we'll see there's a what they call static friction and kinetic friction. And we'll talk about those a little bit. First of all, relate to the fact that the coefficient of friction generally goes from 0 to 1, where 0 is frictionless and 1 is like basically the weight to your own weight. So it generally goes from 0 to 1. So let's pick, like if we have a wooden block and this is a floor, mu might be 0.5, all right? So the friction you have to overcome would be mu times Fn, which would be 0.5 times 980, which would be 490 newtons, all right? So about 50, but this would be about 100 pounds of force to be able to push this thing. So it would take that much to overcome the friction, right? The greater the friction, the more force it's going to take. Now, one thing I'm sure you've always noticed, if we push something like this, pushing this, it's always harder to overcome it at first, but once you get it sliding, it gets easier to do that. So the first part is overcoming this coefficient of static friction, and then you have kinetic friction. So this concepts here, so we have in the table, we have mu s, which is static friction, and mu k, which is kinetic friction, we call sliding friction is a better way to say it. So this is the friction, and mu s is always greater than mu k. So it takes more effort to get it started, but once you get it sliding, it'll slide much easier. And an example of that is we had the wood. That's what it would take to cave, but this would be the static friction, but the kinetic friction could be as low as 0.2. So it takes 490 newtons to get it going, but once we get it going, the friction would be mu k times 980, which would be 0.2 times 980, which would be approximately 190 newtons. So significantly less force to be able to get this thing to go. So this is the concept of static and kinetic friction. And we'll get more into this later when we talk about problems related to rotation. So that's that's the concept here we've had Newton's first law of motion. First, object in motion stays in motion. Second law, F equals ma. Third law is action-reaction. And then we have acceleration elevator. And then we have friction, forces due to friction, static friction, kinetic friction. So on a test, they'll actually give you, what's the values you'll need for that. And we'll talk about this later when we get into chapter 5. All right? So that's basically chapter 4, and we'll go from there. All right? So have a good day.